This video will focus on liquid chromatography. We'll start with a discussion of definitions and instrumentation having to do with liquid chromatography, and then discuss columns, the stationary phase in liquid chromatography, go through some nuts and bolts of pumps, injectors, and autosamplers with special attention paid to the mobile phase composition and gradients, and then discuss some detectors while we also look at some example data yielded by those detectors. We've already seen a crude example of liquid chromatography in the previous video. Here we have a silica stationary phase, and I'm manually applying a mobile phase and pushing it through. Now this is a pretty crude example, but silica is going to be the basis for the column packings in most LC stationary phases. And then we're going to do as we have here, where we put a mobile phase, we push it through with a pump, not with me holding a pipette bulb. And by giving a mobile phase that the compound has an affinity for, it passes through the column and is eluted at the end of the column where it is detected by something besides just us looking at the colors when you're actually doing a real LC experiment. So there is some confusing acronyms and definitions associated with liquid chromatography. So LC is going to be liquid chromatography. And anytime you have a solid stationary phase, it's usually going to be silica based, but anytime you have a solid stationary phase and you are flowing liquid over it to elute compounds, you're loading onto the stationary phase and have a liquid mobile phase, you are doing liquid chromatography. The most common acronym for liquid chromatography in modern experiments is HPLC, which stands for High Performance Liquid Chromatography. You will also see UPLC, Ultra Performance Liquid Chromatography, UHPLC, Ultra High Performance Liquid Chromatography. Now, there's a little bit of semantics here. I'll show you this again later. Like if you take an instrument that is an HPLC, and we say, oh, that's definitely an HPLC, but instead of just connecting it to a UV detector, you take that same chromatography equipment and connect it to a mass spectrometer. All of a sudden, for some reason, instead of calling it an HPLC mass spectrometer, we drop the HP and just call it an LCMS, even though nothing has changed. The ideas behind HPLC, UPLC, and UHPLC are the same. And at different points in history, instead of saying performance, people have said pressure. The real trick here is one of the most important logistical aspects of an LC experiment is you're going to use a pump. You're going to push the solvent. You're going to push the mobile phase over the stationary phase. And to do that, you have to apply pressure. And it turns out, as you'll see, you can get higher performance if you're using higher pressure because you can use smaller particles. But that is to say, you have to have a fancier instrument, a more expensive instrument to go to higher and higher pressures. So what has happened is people have built equipment that can go to higher and higher pressures. So it used to be until very recently that most instruments went up to about 6,000 psi or 400 par, and we would call these an HPLC instrument. That is the instrumentation that we currently have. Recently, the default instrumentation, when you go to purchase a quote HPLC, they're going to say, oh, we have a UPLC. So most commercial instrumentation now goes up to higher pressures, 15,000 psi or 1,000 bar, and they're going to say a UPLC. The distinction between UPLC and UHPLC is hardcore chromatographers will debate and discuss this, but there's a lot of that has to do with marketing. But the basic concept, LC, HPLC, UPLC, it's all the same. You also hear people say, oh no, I have a flash chromatography system, FPLC. It's still liquid chromatography. It's all the same principles when you get down to it. Now, at the heart of a liquid chromatography system is going to be the column. And there are a lot of different parameters that you can adjust about the column. The phase is the big one, or the chemistry. Most of the time, this is going to be non-polar. It's going to be based on polarity, but you can certainly have polar columns, and you can have columns that have to do with ions or size. The length of the column is important. The inner diameter of the column is important. And in HPLC, we are almost always going to deal with packed columns. They're going to be columns just like we saw in that initial demonstration where they are packed with very small particles. It looks kind of like a white solid, but it's actually a bunch of small particles with crooks, nooks, and crannies for the liquid to flow between those particles. This is pretty common for an HPLC column. This is the one that's on our instrument right now. They're going to give you some indication of the chemistry, like that fusion RP, that stands for reversed phase. That means nonpolar. This is 150 millimeter long, 2 millimeter inner diameter, with 4 micrometer particles. HPLC columns come in a fair distribution of sizes. They're typically going to be between 50 millimeters and 200 or 300 millimeters. Here we have a pretty big one. This is actually a size exclusion column, and it's 300 meters long. Here's one 150. Both of these guys are pretty thick. They have pretty big inner diameters. You can see they're wider tubes. It's 100 millimeters. Here we have this is a specific explosives column. So if you look at each of these labels, it's going to tell you a little bit about the chemistry of the column. It's going to tell you how long it is, what the inner diameter is, and it's going to tell you the size of the particles, because these are the critical parameters for these columns. These guys are a little bit smaller, but they can still do pretty remarkable separations. Now, these are pretty boring steel tubes, but inside these tubes, they're packed with small particles on the order of micrometers. The chemistry of the column is going to be determined by what the surface is on those small particles. So silica, for reasons I'll show you in just a minute, is going to be the most common backbone. It's going to be the most common material used to make these. And if you just have uncoated silica, if you just have silica particles, this is quite polar, and this is called normal phase. This is considered normal. And in organic 2, and actually that white column that was in glass, that's going to be silica. Silica is kind of the default for simple, crude organic extractions. What's most common for analytical extractions is actually called reverse phase, with the idea that you have reversed the phase from a polar silica phase to a non-polar phase. And the way that they do that is they functionalize the silica. On the surface of the silica, they attach long, greasy alkane chains. You can also have an ion-based separation with an ion exchange column. Size exclusion columns, those are some of those bigger tubes you saw earlier, are actually based on size. They're almost like giant fancy filters. And then a newer column that has some pretty interesting use, particularly with sugars and things that are very polar. It gives you a little bit better analytical information for polar compounds than a normal phase is. It's called the hylic or hydrophilic interaction. So again, you can see the packing in this. This is very satisfying. It's a glass tube, and you can see that white silica normal phase packing. But you can't apply much pressure to this. This is glass. If we applied high pressures to this glass, it would just explode. So those steel tubes are the same idea as this. You just can't see the column packing inside. You can't see that slurry of beads because you have to have it in a steel tube that can withstand high pressures. So why silica? Well, silica is our material of choice whenever we can because it's one of the most abundant materials on Earth, and it's everywhere. Here's a silica plant in India. It's essentially just fancy sand, and you wash it, you wash the sand, you remove the impurities in an industrial process, and you're done. Now, if we look at the structure of silica, we can see that we have silicon dioxide, 1 silicon, and 2 oxygens. So the little red balls here are oxygen, the central blue ball is silicon. So we have this large crystalline matrix that makes up this big old solid, essentially this fancy sand. So we have this big giant solid. This is our substrate that we're going to use, but really the only interactions occur at the surface. So we have these beads, these tiny spheres. We don't care very much what's on the inside of the spheres. What we really care about is what's at the surface, because that's what the molecules flowing through the column see, is what's at the very surface of these particles. So at the surface of silica, naturally, when this big SiO matrix ends, it ends in an alcohol, and these are called surface silanols. So silica is naturally quite polar. When you have a surface covered in alcohols, it's going to be quite polar. And you've learned a bunch now in chemistry that glass is polar and capillary effects happen. You see a meniscus because water loves glass. Well, that's because glass is made from silica, And glass is covered in surface silanols. So silica is a very polar surface, and that's what makes glass. Now, if we want to make a nonpolar surface, we have to react that silica surface, and by far the most common way to react or derivatize that surface is with a C18 or octadecane. This is extremely nonpolar. Octadecane is extremely nonpolar, also called hydrophobic. So we've taken polar silica and reversed its phase to be very nonpolar. So now things that are nonpolar are going to have a high affinity for the column and take a long time to come out. So the nonpolar reversed phased C18 column, as this is called, is going to be by far the most popular way to do analytical separations with organic molecules. Almost all organic molecules have some affinity for a C18 column. They'll stick at least a little bit, and we don't want them coming out at TM. So we want everybody to stick just at least a little bit. Now you'll notice over to the side here, there's this SiO group on the right that doesn't have any C18s attached to it. That's called end capping. Every once in a while you'll wind up with one of the loose surface silanols that has not reacted with a C18, and that's not a good thing because you have that one little polar group mixed up with the C18, and we don't want that. We don't want to mix a little polar spot with our nice nonpolar surface. It'll cause weird peak shapes and mess up our separation. So most columns will be C18 derivatized, and they will be end capped to ensure that the entire surface is nonpolar and you don't have any of those little excess surface silanols just hanging out, messing up your wonderful nonpolar column. Now, if we look at silica under an electron microscope like we've shown here, these particles kind of vary from 50 to 60 microns or even up to 100 microns. And if we're just doing a simple organic silica column, we don't really care that much about the particles. But the particles, their size and the distribution of sizes and their shape, it's for analytical separations, it's really important that they be homogeneous. They be nice spheres, and they're all pretty much the same size. That's going to give us a really nice separation. So you can see the difference here in these nice, fairly homogeneous, smaller particle sizes that we're going to use for analytical separations. Particle size makes a pretty big difference too. Generally, if you can get away with it, you want to use a smaller particle size. Now, the smaller the particle size, the more pressure it requires, and the fancier an instrument you need. This is where that UPLC and UHPLC stuff comes into play. So we can see here, there are 3 different chromatograms, and they're sort of showing you, here was typical for the 1980s, here was typical for the 1990s, here's typical for the 2000s. In the 80s, and I still use these, 5 micrometer particles were pretty commonplace, and you can see those peaks are a little bit broader, and it takes longer to get the separation done. You go to a 3.5 micrometer particle, the separation gets done faster, and the chromatography is better. Those peaks are not as wide. If you can go to a 1.8 micrometer column, you get nice skinny peaks, and you are done in under 2 minutes. So smaller particles can be really great if you can get away with it. Let's think about why that is. Let's look at this these packed particles right here. These are cannonballs outside of a castle in England. And let's think about if we were a piece of dust or something much, much smaller than these spheres. So as a molecule is to a particle of stationary phase. Particles of stationary phases are on the order of microns, 1 to 10 microns. Molecules are on the order of nanometers. So they're thousands of times smaller. So if we think about these cannonballs and we think about a little piece of dust that was going to wind its way through these cannonballs. Well, now let's think about the Van Deemter equation and those parameters that we went over in the previous chromatography video. So let's think about a piece of dust winding its way through these particles, and let's look at that or think about that in comparison to some other particles. We'll go from packed cannonballs to packed ping pong balls. So now imagine a container packed with ping pong balls. So we're going to compare packed cannonballs to packed ping pong balls. And we're going to think about little particles of dust that are being forced to sort of float or move between those particles. Okay, as our little bits of dust move between the cannonballs, versus moving between the ping pong balls. All right? Think about the openings between the cannonballs and the openings between the ping pong balls. As a little piece of dust moves between the cannonballs and the ping pong balls, for which material, for which packed sphere, are they more likely to touch, more often likely to touch a solid surface? Well, the ping pong balls. They're going to run into the ping pong balls a lot more often. So we can sort of think of this as when molecules are running into these surfaces, when these little particles run into the surfaces more often, I should say when these little molecules run into the smaller particles more often, it's a chance for more extractions to occur. And it provides more opportunity on average for molecules traveling through to do more extractions. That averages out better, and that really helps change or mediate differences in equilibration time. That's that C term in the Van Deemter. So as these particles that are packing the column get smaller and smaller and smaller, the molecules are going to have more contact with more particles more often. And that's going to reduce the problems caused by them not having time to equilibrate, because they're going to have a lot more opportunities to interact with the column. So it significantly reduces the C term as you decrease particle size. It also influences the A term. That was that multiple paths term. You can sort of see here how you don't get as much of a chance to wander off on goofy paths if the particle sizes are smaller. So there's less chance that your molecules are going to take radically different path distances, and that A term is going to also shrink as you decrease the particle diameter. So both the A term and the C term are going to decrease as you decrease the particle diameter. However, the pressure that you have to apply to run the instrument with smaller particles gets bigger and bigger and bigger. That means you have to have a fancier instrument and you have to buy fancier fittings, and that gets more expensive. So here's our friend, the Van Deemter curve, and let's look at a simulation of what happens when both the A term and the C term decrease as we decrease the particle size. There's a few important points here. First of all, the overall efficiency, the plate height got much better. It got lower. The minimum plate height got lower because that A term is dropping. Second of all, when you decrease the C term, the slope on the right side definitely flattens out. And what that means is, even if you go beyond, even if you go faster than you should to hit the minimum H, you don't get penalized much. So you can go faster and your chromatography doesn't suffer much. So when you have smaller particles, you can go faster and still get great separations, get better separations. But again, the trick is, the smaller the particle size, the more pressure your instrument has to put out. And then if you have small particles and you want to go fast, you have to put out even more pressure. So here are the most common commercially available liquid chromatography systems. And you can see there are some different criteria that differentiates them, but probably the biggest thing that's going to differentiate these liquid chromatography systems is the maximum pressure that they are capable of pushing. So basically, you're going to pay more for more pressure. If you want to use smaller particles and you want to go faster, you're going to get better chromatography faster, but you're going to have to pay for it. Okay, so we went over some basic definitions. We talked about columns. We talked about a little bit about their chemistry and their length, inner diameter, and we talked about particle size. So now let's focus on a pretty nuts and bolts part of the instrument, and that is the pumps. You've heard me talk a lot about pressure. The pumps are going to be what you're going to use to apply the pressure to push the solvent through. The injectors, because you got to get the sample in the system. And then we'll also spend a good amount of time talking about mobile phase composition and gradients. Here's a nice schematic of an HPLC system. You have to have mobile phase reservoirs. This is really just going to be big containers. Most of the time you just use the container that the solvent came in. So these are big solvent containers full of plenty of mobile phase. Then you have to have what's called a degasser. That's a lot more important than you think. It turns out when you're pushing liquids at high pressure, bubbles are a huge problem, and bubbles will ruin your chromatography. This used to be a much bigger issue. You used to have to do a lot of manual labor. You had to bubble your solvents with helium. They called it sparging before you ran. It was a lot of work. But for a long time now, HPLC systems have had these really nice things the lines run through called degassers, and they get the bubbles out of the lines for you, which is wonderful. Then you're going to move into the pump. The pump has to have some kind of controller to control the speed in the mixing. Then you're going to run into an injector, or what's called an auto sampler, that's going to get the sample into the system through the column. Now you see here the column is in a column oven. This is not like GC. The oven is at the heart of the GC, and temperature is all important. This oven is important, and you can kind of warm up the column. Sometimes people go like 50, 60 degrees. But here, I want to point out a really big pitfall for students here. When we're talking about method development and I'm asking you on an exam, how could you fix this method? Do not say, oh, well, I'm going to run a temperature gradient with the column oven, or I'm going to raise the temperature to 250 degrees. That is a terrible idea. Column ovens for LC won't go that high for good reason, because they're liquids, they'll evaporate, and we just don't do that. You can warm things up a little bit if you want to, but it's not a super important parameter in LC, and we don't change the chromatography significantly in a controlled way using the column oven, okay? So it's there to hold the column and maintain it at a consistent temperature because we don't want shifting peaks. And then you have to have a detector, and then ultimately the liquid flows out to a waste container. So here's one of our HPLC systems, and you can see our mobile phase reservoirs, just big bunches of mobile phase up top. We have an auto sampler right there. The column is on the right in the column heater. The degasser and the pump come in one unit, and then our detector, this detector is a UV detector, is just sitting there beneath it. And this crude schematic gives us a little bit of a sense of how things flow through the instrument. That we actually have 4 solvents, and we have one pump that can pump 4 solvents. It's called a quaternary pump. But we pull the solvents, solvent A, solvent B, through pump. They mix in the mixing chamber. They go to an injector valve, and that helps. You put samples in the sample tray. The injector pulls the samples from the sample tray, pulls little bits, injects it onto the column, and then it goes out from the column to the detector. We'll look at that in more detail. So you're going to see a lot of the thermo liquid chromatography systems. That's what we have. I am a big fan of the thermo systems. Ours are a little older, but you can see they all look pretty similar. Logistically, they're going to make these into stacks, so they don't take up much space on the bench, and then the gravity helps the solvents flow. So you can see they have kind of the basic shape for all these different commercial varieties. They're going to be modular, and they're going to be these stacks with these different units that stack up on top of each other: pump, auto sampler, detector, degasser, etc. So you saw that other HPLC stack that had a UV detector. This is a similar stack. It has a UV detector, but it also has that mass spectrometer, that big box next to it. And this is going to be your primary workhorse next semester. This is what you're going to use for LCM, SMS, and toxicology. It was donated by the medical examiner's office. It was actually the instrument that they used to run their cocaine quants on. So let's use this instrument as an example, and let's walk through it in a little bit more detail. So our pump unit's on the bottom here, and if we open up the covers, we see these piston valves inside, and we see these tubes labeled ABCD coming in from the solvent up top. So we've turned the pistons on, we've turned the pump on, and these pistons move back and forth, and they pull solvent in a very controlled way from those bottles of solvent up on top. And the pump is what really makes the system work. The pump and the column are 2 of the really core parts. These pistons are going to pull liquid through the column in a very controlled way with a controlled flow rate, and it's also going to help us mix these solvents in a controlled way. These piston pumps operate a lot like hand pumps that you just sort of move up and down. You see well pumps and things. And this is a nice video made by these Serum Hydraulics. You can see there's this check valve. You pull up the piston, and it draws up some water. But then when you push down, that valve prevents the water from going out the same way it did. It goes out through where you want it to go. So you pull up, and you draw from the reservoir. But then the trick is you have these what are called check valves that keep the water going where you want it to go. So this is a hand pump. You sit here and you do this. Water goes in, water goes out. This is the same principle as those pistons you just saw. It's just we're using motors to do the pulling for us. Okay, so here you can see the pistons pushing, and this is a valve on the output that I have opened up so that it's not going to the column, it's going to here. And you can see these guys pushing against the back pressure. And we often use this syringe to make sure that we're putting out what we're supposed to be putting out. This guy's at 2 mils a minute, so you can sit there with a timer and you can watch the syringe fill up. These pumps can push against back pressure. Remember, that's one of the main things you're paying for when you pay for an HPLC system, is how much pressure can you put out. So they can push against back pressure, and they can actually kind of push this syringe down. So over the course of a couple minutes, this guy should hit 2 mils because it's at 2 mils a minute. So if we cheat and speed this guy up a little because it's boring, you can see it fills up the syringe pretty quick. Okay, so if we close that valve, so now the syringe is pushing out, let's trace the flow of liquid a little bit. The pumps pull the solvents from the mobile phase into that ABCD. We're usually just going to use solvent A and B, almost always just going to use solvent A and B. Now between that A in and A out and B in and B out is the degasser that gets rid of the bubbles. And then those 4 little plastic things are actually check valves. They get pulled into a mixing chamber so we can change the proportions of the solvent. And this turns out to actually be really important. This is our mobile phase. Whatever comes out of here, whatever exits this mixing chamber is our mobile phase. But we can change the composition of our mobile phase. Usually we're going to run A and B solvents, and it's really simple for us in the software to just change the percent A and percent B and change the chemistry of our separation. So that's going to be an important part of the method, which we can change to software. You see right now we have 50-50 water methanol with 0.1% TFA, and we can easily change that to 80-20. We just do that in the software. So it's really easy to tweak our mobile phase composition in the software because it's so easy. That's probably the thing we do most often when we want to fix our separation. It's the easiest thing, and remember, do the easiest thing first. See if it works and see if you can get away with it. Let's take a look at how changing the mobile phase composition changes the separation. So here we have, this was done in our instrument a couple years ago. I made a mixture of 9 explosives. It's on a column specifically made for explosives. It's the Acclaim Explosive Z2. 4.6 millimeter inner diameter, 250 millimeters long, 5 micrometer particles. And I used a methanol water mobile phase. So water is going to be solvent A, methanol is going to be solvent B with a UV photodiode array detector. So same stationary phase, same flow rate, same everything. What we're shifting is the percent B, the percent methanol. So at 48% methanol, you see those 9 peaks. They do elute. There's nice separation. But when you see that big gap, like between 6 and 7, you don't need that much resolution. At that point, you can sort of think of it as you're wasting time. If you could push those peaks closer together and still keep that resolution, you could save some time. So one thing we can do that pushes all the peaks to elute faster is use a stronger eluting solvent. And methanol is the stronger eluting solvent. It's slightly less polar than water, and this is not a C18 column, but it's based on polarity. It's a non-polar column tuned for explosives. So you see we increased the percent methanol to 60, and 7, 8, and 9 are looking gorgeous. They come out much faster. 6 looks good, 5 looks good, 4 looks good. But then 1, 2, and 3, we've pushed them too much, and now those peaks have squashed into each other. If we get even more ambitious and go to 70%, it looks like we still have 7, 8, and 9 barely resolved, probably, and this stuff comes out much quicker than it did in our first separation. We're done in under 10 minutes, but we've lost definitely 1, 2, and 3, and then maybe 4. So 70% definitely isn't going to work. 60%, if we're focused on 7, 8, and 9, 60% is great. But if we want everybody resolved, we have to stick with 48% methanol, and we have to go for a long time. We had to go for these 35-minute runs. Now, what we would like is we would like to have a lower composition, lower percent B, while those first few compounds elute, but then increase the percent B to push those last 7, 8, and 9 peaks, those last explosives off faster. But there's no reason we can't do that. We have this whole fancy pump system, so we don't actually have to keep the percent B the same the entire time we're running. Just like we can adjust the temperature of a GC run during analysis, we can adjust the percent B, the mobile phase composition, in the middle of a run for HPLC. That's one of the things that we program in. and this is called a gradient, running a gradient or gradient elution. So let's take a look at an example of where a gradient can be really nice. So this example is from a really nice website called Chromatography, and they're doing a separation of 16 different compounds. They're polyaromatic hydrocarbons. They are on a 100 millimeter long column, 3 millimeter inner diameter. They're doing acetonitrile water. So water is A, acetonitrile is B, 1 millimeter a minute. And they started with 70% acetonitrile, 30% water. This is called isocratic. They ran the same mobile phase composition the whole time. The previous runs I showed you for the explosives, those were also isocratic. Same mobile phase composition the whole time. This has a lot of problems. 1 through 8 are kind of a mess. Peaks 1 through 8 are kind of a mess. 9 and 10 look pretty good, 11, 12, but you can see 11 and 12 are broadening. We want to fight that if we can. By the time we get to 16, they're really broad, and it takes a long time to come out. So we have too much percent B. We have too much acetonitrile in the beginning, and we don't have enough in the end. We want the beginning peaks to spread out a little bit, and we want the last peaks to get pushed closer to TM. So we want to start at a lower percent acetonitrile, but then change the composition as we go through the run to allow those first peaks to elute resolved, and then those later peaks to get pushed off quicker. So let's see what happens when they ran this gradient run here. So you can see now there's still acetonitrile water, same column and everything, but they programmed in from 0 to 5 minutes. We're going to start at 50% acetonitrile, and then we're going to ramp to 100% acetonitrile with a linear ramp between 50 and 20 minutes. So this is a linear gradient. So they started at 50% acetonitrile, which is actually kind of a lot, ramped up to 100 so over the course of 15 minutes, they ramped gradually from 50% acetonitrile to 100% acetonitrile. And you can actually calculate out what percent B that would be a minute by taking 50% and dividing by 15 minutes. But you can see here, this is beautiful chromatography. They're not getting done too much faster, but they didn't even have the peaks resolved with the isocratic run. But here they have everybody pretty nicely resolved, and there's a lot of compounds in there. 3 and 4 and 9 and 10 are close, but the chromatography here is much, much nicer. The peaks haven't broadened out as much at the end because they've pushed them out quicker, and those first peaks aren't all crammed together. So gradient elutions are really nice when you're running a mixture where you have a wide variety of polarities in your mixture, some polar things and some very non-polar things. And we can see here, this is just a schematic of kind of what a gradient looks like. You're going to start off at a low percent B. You're usually going to have a hold, and then you're going to ramp to some higher percent B. Now, the bummer about running a gradient is it's much slower than an isocratic, than just keeping it the same percent B from run to run to run. And not just because you have to take the time to run the gradient, but when you're done, you need to do 2 steps that are not very glamorous, and they serve no real analytical purpose. You got to do a wash step. You got to hold at a really high percent B, and that's to make sure that if you're running nonpolar things, you need to push junk off the column and make sure nothing got stuck on there. You have to wash the column. A lot of times you'll just turn the detector off for this step. And then you have to program in what's called re-equilibration. Because if you just stop the run, if you stop run number 1, if you're running 10 runs in a sequence, same method. Run number 1 goes up to 80% acetonitrile. Okay, so at the end of run 1, you're at 80% acetonitrile. The instrument will try and immediately drop down to 5% acetonitrile. Now the truth is, this is a liquid. It can't mix that fast. It can't flush all that acetonitrile out of the system, and it doesn't. But on the software, it'll say, okay, I'm at 5% acetonitrile, go. It is not. It's a weird mixture somewhere between 80 and 5%. You have to give the instrument time to flush out all that excess acetonitrile and re-equilibrate back down to 5% acetonitrile. If you do not, you will see your peak times shift, and that is terrible for us because our major point, remember, we don't do a lot of quantitation. We do qualitative analysis. It's based on the x-axis, which is time. And so if our peaks if we're running standards and the time for our standards is shifting from run to run, then that ruins our qualitative analysis. So this re-equilibration step is really important, but it takes time. It takes extra time that's just wasted. It's not analytical time. You turn the detector off and you're just letting the instrument re-equilibrate so that it's ready for the next run. In GC, if you run a temperature gradient, the GC also has to do this, but it's an oven. It just opens up the back of the oven and blows the hot air in the room, and it goes much quicker. So it's much quicker if you can get away with it, if you're going to run 20 runs, to just run an isocratic run. But the things you're running, you need one or two things, or everything needs to be pretty close in polarity. So when you have things that are very different in polarity in a mixture, you need to run a gradient. Let's look at one example of doing this with software. So we're starting off here at 80% water, 20% methanol. We're using methanol as our percent B, and that's what you want to start off with, a low percent B. We're at 20%. And what we're saying is from 0 to 2 minutes, hold at this 20%, and then gradually over the course of the next 10 minutes, ramp up to 95% B, and then you can see that big long re-equilibration step we have at the end. So if we look at the summary of this method, we have A is water with 0.1% trifluoroacetic acid, common additive in HPLC. B is methanol that also has 0.1% trifluoroacetic acid. We're going to control the pH, and that's what is called an ion suppressor. We hold at low 20% B for 2 minutes, and then ramp linearly to 95% B from 10 to 12 minutes, and then hold for 2 minutes until 14 minutes. Then we turn the detector off, drop it down, and re-equilibrate to 10 minutes. So we have kind of a wash step, and we do have a re-equilibration step. So if you want to change your separation, if you're not getting peas to separate, you want to start with the simplest thing first, and that is change your mobile phase. Change your percent mobile phase. That's very easy to change in the software, very easy to play with. It's like temperature in GC. So start there, and if you can't do that, then you have to start changing columns and things. So let's get back to our plumbing here. And we had the pump. We had the mobile phase exiting the pump. We talked about how you can mix that up. Now let's look at the rest of the system here. We have the mobile phase being pulled up into that little black guy there, that little injector valve. The output from the pump goes into the injector valves. Now, valves are not the most glamorous things, but they are important, and we need to take a look at them and how they work, and they can be a little bit confusing. So here's a manual valve removed from the instrument. It has a hole in the center that you can put a syringe in, and you can squirt sample into it. It's called loading the loop. After you've loaded the loop, when you're ready to go, when it's go time, you flip the valve from load to inject. Let's look at what happens with that valve. The real workings are on the other side when you flip from load to inject. So you have it in load, there's a loop that you fill with sample, and then you flip it to inject. Here's the business side of the valve, and you see it has these positions labeled 1 to 6. And I didn't have anything connected to those, so you can see it nice and easily. But let's take a look at the schematic to see what happens. When you have those two positions, the whole point of the valve is it switches who is connected to who. So you can put tubes in each of these positions, and you can decide who gets connected to who, and then you switch the valve, and it switches who's connected to who. So when the valve is in the load position, 1 is connected to 6. 1 flows into 6. 2 flows into 3, and 4 flows into 5. But when you flip the valve to the inject position, it switches who's connected to who. Now 1 is connected to 2, 3 is connected to 4, and 5 is connected to 6. So the trick here is you connect them up very carefully. At first, you connect 2 and 3. So 2 comes from the pump, 3 goes to the column. So what's happening is that when it's in the load position, the liquid is coming in from the pump and just getting pushed straight to the column. So it's just a river of solvent flowing from the pump through the column and then out to the detector and then ultimately out to waste. And 1, 6, 5, and 4, they're just sitting there on the side, not really connected to the system. But 1 is connected to 6, and then you make 1 connected to 4 with what's called a sample loop. Now this loop is going to be a piece of tubing that you very precisely know the exact volume, and that's going to end up being the volume of sample that you inject. So you purchase these loops with little tags on them, and they're pretty precisely calibrated, pretty accurately calibrated to say 10 microliters or 5 microliters. So the volume of that tube is 5 microliters. So you connect this tube between 1 and 4. Okay? Now, when you put the syringe in the needle port, it pushes through 4, through 1, it pushes through the sample loop, and then it pushes to 6, and they say vent. That's just waste. 6 is going to waste. So you actually fill up that loop, and you keep going. You watch it squirt out of 6 and into the waste to make sure that you've filled it up plenty. So you've now completely loaded that sample loop with sample, and you say, aha, I know that there is 5 microliters if it's a 5 microliter sample loop. Now when you're ready, when everything is ready, and it's go time, then you flip the switch to inject, and now the flow from the pump at valve 2 is connected to the loop. So it flows through 2 and pushes the sample out of the sample loop and onto the column in a nice tight sample plug, so that you get this good sample plug and you don't get any band broadening, or you don't mess up your sample plug at the beginning. You get a good tight sample plug. Now I have run an instrument with a manual valve, but that's actually not very common. What's more common is this guy. You see the 6 positions here, but it's got a motor on the back. It's got a motor on the back with some connectors so that the computer can switch the valve for you. Okay, so let's take a look at the auto sampler and that valve system here. We have positions 1 through 6, just like we saw. And then we have this injector syringe. So we're not going to put a syringe in a loop by hand. We're going to have this guy do it for us in an automated fashion. So let's watch this happen. So first, this guy, the needle moves to the vial position. It punctures the septum in the vial. So I put it in A1, position A1. So, and then our syringe, if you watch in just a minute, the syringe is going to pull down a little bit and pull some of the sample out of the vial. So it's loaded with sample. That syringe is loaded with sample. Now, the needle connects to the sample loop, and the syringe pushes it into the sample loop, so it's loaded. Now we'll speed things up just a little bit because that makes sure that it's all ready. But once it's nice and ready, and it's go time, then it's just gonna, you actually hear it go bzz. It's a mechanical switching of the valve. It switches the valve and to the inject position, and that pushes the sample from the sample loop onto the column in a nice tight band. Okay, so we've gone through definitions, instrumentation, we went through the column chemistry, particles and things, then we went through the nuts and bolts of the pumps, injectors, and auto samplers. Let's finish up with a discussion of detectors and look at some example data. Let's go back to the instrument again and just see, there's the end of the column from the injector valve, it comes out the other end, and then it really is just a tube that you can kind of connect to what you want. So if we take that tube right here, you can see that red tube is coming out of the column, and there's the drip, drip, drip of the controlled column flow rate coming out that tube right there. I don't have it connected to any detector right now, but you can essentially just plug that tube into whatever detector works, and you are in business. It's a lot easier to change a detector, to mess with a detector in LC than it is in GC, where it's integrated into a gas system. So here we have a UV vis detector, a photodiode array up top, and then that big box right there is the mass spectrometer. And we can really just take the output from the HPLC. This is also easier to do because we're at lower pressure. And we can just connect it to the fitting in the front of the UV-Vis photodiode array. And then we'd be doing UV-Vis. But we will disconnect that guy. And we can then just hook it up to the mass spectrometer, flow it into the mass spectrometer. You can actually also hook it into the UV and then have the output from the UV go into the mass spectrometer, so you're using both the UV detector and the mass spectrometer if you want. So a quick note here, this tube that I have right now running out of the LC and the detector is really too long. You want to keep that as short as you can. It's a really small inner diameter tubing. But the more volume you have between your column and your detector, that's called dead volume. It's not doing anything for you. The separation is done. So all that's happening in that volume is band broadening. And you can see in this figure here that's called extra column dispersion. You can see in figure 1, they've kept the tubing nice and short, but as that tubing gets longer and longer, you actually ruin the chromatography that you worked so hard to make. So where you can, you want to keep the end of the column and the input of the detector as physically close as possible with as little volume tubing as you need to connect those two things. We don't see much of a difference in the system, and it's very convenient to just be able to unplug this guy and plug it into whatever we want. So let's take a look at some data. We'll look at data that was both taken using a UV-Vis spectrophotometer as a detector, a PDA photodiode array, and a mass spectrometer detector. So this data right here is a mix of papaverine, dextromethorphan, and indole. All right, and we can see we have 3 peaks eluded here. We have chromatogram data up here with intensity on the y-axis, time on the x-axis, as we normally expect. But the trick is with this data, when you have something that can give spectra in and of itself, so a UV-Vis spectrophotometer can give 2-dimensional data in and of itself. So this is the chromatogram, but if I click on the chromatogram, you see down here, it shows me the UV-Vis spectrum for that specific point in time. So I clicked here at 10.84 minutes, and it says, okay, this top piece of signal here has a signal intensity of 1.91 e to the 5th. The e often is, when you have trouble in computers, writing 10 to the, so it's 1.91 10 to the 5th times 10 to the 5th is the intensity of the maximum signal. And I can click around up here, and at each point in time, I'm getting a spectrum. So this is really powerful data. This is what we call 3-dimensional data, because I have X, Y data for signal intensity and retention time, but I also have X, Y data at every point in time for wavelength, which gives me identity and intensity. Okay? So what the instrument is really doing is it is taking a full scan, a full UV-Vis spectrum, which in and of itself is data that can be used for identification. It's not great for identification. It's a, I believe, category B, maybe a category C. I'll have to check on that. But it does give you some information about identity, where the peak is on the x-axis. Now, the peaks in UV-Vis are very broad, so that doesn't give you much information. Okay, but if we look here, here's the name of the run we're doing. See this number 1? That means at time 0, boom, at time 0, it took a scan. Retention time 0 took a scan, and there's no signal. Okay, now we're going to step through. Now, as soon as it was done with that scan, it took another one, and another one. Oh, there's a little bit of something in that one. So this is scan number 3, 4, 5, 6. So for each point in time, so watch this number, and you're going to see it's taking a scan as quickly as it can. Okay, it's taking scans as quickly as it can. So as we pass through, it just sat there and took full UV-Vis spectra over all this point in time. Okay, so it's scanning all the way. Now we're at scan 378 at 1.26 minutes. Now these points are discrete. Let's look here. This will be a little bit easier to look at. These points are discrete. So if we look at scan number 1700, it's at retention time 5.66. The next scan was at 5.67. Next one at 5. There's not enough resolution here, and it goes out to this decimal place. But if something happens between scans, we'll miss it. So you have to scan really fast. Now it's a little bit deceptive here in the data, because this is not a continuous line. This is dots for, let's click. This is spectrum 1596. That's spectrum 1597. We'll zoom in even more. Let's zoom out just a little bit there. Okay. Spectrum 1588. That's spectrum 1589. That's a dot, and it's drawn a straight line. It didn't catch anything in here. It's busy. It collects this spectrum, and then it takes this amount of time to collect spectrum 1589, 1590, 91. But this is pretty remarkable. So you got to be quick. You got to scan quick, but this is pretty remarkable because at every point in time, you get a full spectrum that can tell you something about what is in there. So what can be powerful is if we click on the peaks, this thing has again, we're not going to get too deep into UV-Vis. We'll spend a good amount of time in that in spectroscopy at the end of the semester. Same thing with mass spectrometry. But for right now, you can see that we know that XY data, instrumental data, gives you identity information. So this guy has this broad peak at 266. And that looks quite different than this guy that has this peak early on. Lots of things have this peak over here. But then it has this peak at 310. That's a little bit different than this guy who has a peak at 278. So we get information potentially if we know what we're looking for, if we know what the UV-Vis spectrum of compound supposed to be like, we can get information not just from the retention time, like you guys have been doing with the GCFID, which does not give you a third dimension of data. We don't just have to use retention time. You can use information from the spectrum that was acquired. Okay? Now, when we get data like this, where at each point in the chromatogram, we have a full spectrum, we also have a second bit of instrumental data at each point, we have to figure out how to plot what's on the y-axis. Okay? Because there is no one data point for this. Here at 4 scan 1948, it is saying the intensity. If we look down in the corner, you can see it says, oh, the intensity here is 3.44 e to the plus 003. So it's saying on the chromatogram the intensity here is 3,400. Well, where is it getting that intensity from? Where is it getting that intensity from? Is it taking it from here, 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 here? And the answer is, if we look at the peak here, it's taking the top intensity in the spectrum, and it's plotting that on the y-axis here. But there are different ways to display the data, and this can be really powerful. Okay, so say this guy over here is kind of little. If we wanted to see a little bit better, we could say, you know what, instead of plotting just whatever the top point is on the spectrum over here, let's plot the signal intensity at wavelength 278. Okay, so this is the same data. We're not running a new spectrum. I'm just going to plot it in a slightly different way. I'm going to say, that's called the total scan. Now I'm going to say, you know what? Plot this as the signal intensity at 278. And you can see that changes our spectrum, not a whole ton, but it changes our spectrum a little bit. These guys also have absorbance at 278. That 278, 280 region is really common. But now it's plotting the signal intensity over here. You can see the y-axis has shifted because it's plotting the signal intensity simply as, well, what is your absorbance at 278? So at this point in time, it's measuring the absorbance at 278. And then it puts that as this point on the y-axis up here. All right, this guy has a peak at 310. And that's a little bit unique. That's further out than these guys go. So if we change this to be, you know what? Show us the signal intensity at 310. Those things seem to have disappeared. They're still there. It's just the way that we process the data. We said, okay, for this plot, for this second plot here, I want you to plot on the y-axis in the chromatogram, plot the signal intensity at 278. And the only thing that has appreciable signal intensity at 278 is this guy in the middle. And I believe that is indole. So if we say that's indole, indole is the only thing that has appreciable signal at 278. If we look at this guy's spectrum, I'm sorry, not 278, at 310. We plotted it as a function of 309. So if we look at this guy over here, there's not much going on at 309. So there's not much there in this way of looking at the spectrum. Same thing here. We know that there's a peak here because we see it here, but there's not much going on at 309. We're far away from the peak. So when you have three-dimensional data, as we call it, when you have a chromatogram where every point on the chromatogram represents another full set of instrumental data. So like I said here, every bit of data up here is actually a complete UV-Vis spectrum. And there's a lot of things that you can do with that. Okay, when you have this three-dimensional data. UV-Vis detection is going to be cheap and simple, and it works for most things that we're interested in. We'll talk a lot more in spectroscopy about what kinds of, or how UV-Vis works. But what you want to know right now is UV-Vis is cheap and simple, and it's relatively quick. You have to be fast. If you use a photodiode array detector, it's fast because you have to be fast. You have to be able to get a full spectrum. See, this detector can get a spectrum in under 0.01 minutes because the difference between these spectra, it's getting, let's see, if we go back here. Okay, so the first spectrum here at 6.95 is 2085. So during 6.95, it gets 2085, 2086, 2087. So in that 0.01 minutes, it got 3 spectra. So it can take spectra pretty quick. Otherwise, you start missing data points. You could miss peaks or miss parts of peaks, or it could malform your peaks if your detector isn't able to keep up with the chromatogram, keep up with time. So UV-Vis with a photodiode array detector, a PDA, is fast enough to work as a detector for UV-Vis. The thing about UV-Vis, though, is your stuff has to have what's called a chromophore. It has to be able to absorb ultraviolet light, which means it has to have at least some conjugation. And you guys did great on this in the review problem set, so I'm not going to go into detail about what conjugation is, but the more conjugation something has, the more the detector will respond to it, the more of a response it will get. Because a lot of these drugs have phenyl groups, almost all drugs are going to give pretty good signal on a UV. But you would not say, you know what, I'm going to look at fire debris on an HPLC with a UV detector. There's a lot of different issues there, but a big one is a lot of the stuff you're going to look at for fire debris, alkanes, alkenes, cycloalkanes, essentially all these aliphatic hydrocarbons are not going to absorb in the UV, and they're going to be invisible to the detector. So it's great for most organic molecules, because most organic molecules do in fact have some conjugation, but to be seen at all by a UV-Vis detector, you have to have some kind of conjugation. We're going to look at some mass spectrometry data now, and again, in a little bit, we're going to spend a good amount of time on mass spectrometry. For right now, you don't need to have an in-depth understanding of mass spectrometry. I'll give you a very cursory explanation, but I do expect you to understand it as explained in this video. So we won't get into the mechanisms of how this happens, but for the most part, there are different types of mass spectrometers, but the type of mass spectrometer that you hook up to an LC to use as a detector is going to give you the signal for essentially the molar mass of the compound. So if we click here, we get this big peak at 316, little peak at 317, 318. These are called isotope peaks. Again, we'll explain that also. But we get this big signal at 316. Now, mass spectrometry is quite powerful. We're going to be able to tell what this is, or have a very good idea of what it is based on this spectrum. This type of mass spectrometry that we're using right here is not, they actually sort of debate this in SwigDrug, but the way that we have this mass spectrometer set up, it's not exactly category A. There are a lot of things it could be. It's a pretty strong category B, but just to say that something has a molecular weight of 315 certainly doesn't tell you the identity unambiguously of that compound, but it is a lot of really good information. So we get this peak at 316, and that is a peak in this type of mass spectrometer. You get the protonated molecule. So we spend a lot of time saying that bases accept a proton. Well, when they accept a proton, they gain a mass of 1. So when I see this peak at 316, it means, okay, that's a thing with a molar mass of 315, but it has accepted a proton, and it is giving me a peak at 316. If I look at my list of suspected compounds, then the only thing that has a molar mass at 315 is oxycodone. So this guy is very, very, very likely oxycodone. All right, so if we look up oxycodone, and Wikipedia has good information for these things. There's a structure. Its molar mass is 315. So the protonated molecule if we take 315 and we put an H plus on there, and H plus has a molar mass of 1, then we get 316. So that peak of 316 is very likely oxycodone. Now, you might say, well, it's definitely oxycodone, but this is another good resource, by the way, the NIST Chemistry Web Book. NIST is a federal agency that keeps analytical data, makes standards. It's a really, really good. They make most of the libraries for most of the mass spectrometers, or they are responsible for compiling them, I should say. But you can search known compounds by molecular weight. So what we are going to say here is, okay, let's search. We know it's rounds to 316. We're not sure much more than that. So let's say, okay, everything from, everything from 315.5 to 316.4. Show me all those. So there are a list here of 400 possible compounds. Okay, but still 400 over 40 million or whatever that number is. This is pretty good. And then of these, only a few are going to make sense. So as controlled substances, only a few of these are actually going to make sense. And let's see, oxycodone should be on this list. Might be under a different name. Yeah, so it was on that list, but they must have had it under a different, maybe under the IUPAC name or one of these names. Okay, so I ran this mix. I know that oxycodone was in there, but just looking at the chromatography, even if I know what these 7 or 8 compounds are, these 7 compounds are, you can't look at a peak and tell what it is. But if you have a mass spectrometer, and I know that I had oxycodone in there, then nope, that's definitely oxycodone. I know I had 304. Okay, cocaine has a molar mass of 303. Protonated molecule has a molar mass of 304. So this is my cocaine peak. So mass spectrometry is extremely powerful. Heroin has a molar mass of 369. Protonated molecule 370. And benzylecgonine, molar mass of 289. So protonated molecule at 290. So I can go through each of these peaks and pick out the identity of the compound based on the mass information that I get from the mass spectrometer. So what you want to know about mass spectrometers at this point is the kind of mass spectrometers that you hook up to the LC in a technique that we'll call LCMS. Now, again, we learned in the vocabulary, don't get confused here. Nothing has changed. It's the same HPLC unit. It's just weird that we dropped the we don't call it HPLC-MS. We just say LCMS. It's the same unit. It's the same everything. But as soon as you hook up to mass spectrometer, for some reason, we're like, that's an LCMS. We're going to drop the HP for some reason. But this is LCMS. LC with an MS detector. So this is really powerful. It's much more useful than UV. UV, you can get a lot of different compounds for similar UV spectra, and you can't just look at the UV spectrum without doing a standard and tell what it is. But we can go look up molar masses, so this is very, very useful. Okay, so first of all, let's clean this spectrum up a little bit. So if we look at how the y-axis here, mass spectrometry is a little bit different because we always do what's called normalize the spectrum. So they take the tallest peak and call it 100%. And then they show you the relative abundance. That's the nomenclature. That's what's standard in mass spectrometry. It's a little bit different. So they take the tallest peak, call it 100, and then put everything relative to that tallest peak. Okay, but this is a pretty ugly spectrum. The first thing is, really, this run ended at 8 minutes. But stop here and think about I should have turned the detector off, because the rest of this is not analytically useful. Okay, I've left it on this spectrum because I want to show you something, but the rest is not analytically useful. If my run was done in 8 minutes, why would I keep going? Why would I keep the HPLC going? Hopefully you said, you know what? he's probably cleaning and re-equilibrating, as we talked about before when we talked about pumps. Yep, I cranked this up to clean off anything that might be left in there, and you can see some stuff came out, and then I re-equilibrated for a few minutes. Okay? All right, now if we look at how it is getting the information for the y-axis right now, it's what we call a total ion chromatogram, or the TIC. So what they are doing is, if we look at any spectrum, so this is the very first spectrum that it acquired. This is going to be just like the UV, where you get a full mass spectrum at every point in time. So this is spectrum number 1, and then we can watch here as we cycle through spectrum 2, 3, 4, 5, 6, 7, 8, 9, 10, and the retention times are increasing. Now the mass spectrometer is a little bit slower than the UV detector, so you really only get one spectrum, maybe 2 per every 0.01 minutes. But we can see this first peak is scan number 245, 245. Second peak here, the oxycodone peak, is scan number 350 at retention time 1.64. Okay, so we have a full mass spectrum for anywhere we click up here. But it has to pick something. It has to pick a way to display Y intensity on the chromatogram. So the default is, again, going to be the total ion chromatogram. So the default is not going to be, oh, pick the tallest peak. And so the tallest peak here has an intensity of 4.13 times 10 to the 4th. That is not what the default typically is with most software with mass spectrometry. It's called the total ion chromatogram. So what it's actually going to do is it's going to take the intensity for every, this is all noise. All right, the intensity here is 4.3 times 10 to the 4th. That's not a big intensity. If we look at the intensity of these taller peaks, they are all the way up at 10 to the 6th. Okay, now you can definitely see the noise. And the way we have it plotted right now, we are working in the signal to noise, 10 to 100 kind of ratio. But if we look at this is noise. All right, this is just noise. But what it's going to do is it's going to take the intensity of every single peak. So this little guy right here has an intensity of 4 times 10 to the 3, and it's going to take every single little noise peak or every single little peak in the spectrum, and it's going to add them all together. It's going to say, okay, this intensity, this peak, plus this one, 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 and it's going to go through and add up every single peak. And then when it's added them all up at the end here, it's going to say, okay, here is the total intensity of all the peaks added together. So now I'm going to put that intensity as the point right here for scan number 1. The y-axis is going to be the total for all the ions. So we call this the total ion chromatogram. All right. Now I'm operating here at pretty low concentrations of these drugs and metabolites. So the signal to this is what's called the MS1, a little bit less sensitive, still way more sensitive than UV. But I am I'm getting a lower signal to noise here, but there's tons of ways for me to play with this chromatogram. So the first thing I'm going to do is do something similar to what we did with the UV data. I'm going to tell it, don't show me the total ion chromatogram. I don't want you to show me the y-axis as the sum of all the peaks in the mass spectrum. Instead, I want you to pick the tallest peak in the spectrum, which is called the base peak, and let that be the intensity. You know what, we'll show both of them just to show the difference. I want you to pick the base peak, the tallest thing in the spectrum. So there we go. You can see there's an enormous difference in the signal to noise when I say, just plot this chromatogram as a tallest peak in the spectrum. And look, this bunch of junk here, this stuff is the stuff that washed off the column during the wash step. This is basically gone, even though it's huge in the total ion chromatogram, because there's a bunch of different things in this junk that washed off. There's a bunch of different moderate intensity peaks, but there's no one peak that's really big. So up here, the signal was add all these together. Down here, this little bump is just this guy, just the tallest peak in the spectrum, 3.62. Now this guy, before, it was accounting for all these little peaks and adding them all together. Now it's just taking the intensity here. So you can see the way we look at the chromatogram makes a very big difference. All right, so let's get rid of that tick. total line chromatogram and just look at the base peak. Okay, much better. So here's another wonderful thing we can do with mass spectrometry. We did this a little bit with UV, but because you don't get nearly as much information from a UV, it's not nearly as selective as mass spectrometry is, this is going to work a lot better with mass spectrometry. So first of all, these 3 peaks are definitely not completely resolved, but we think there's 3 peaks there, but we get to see for sure. Okay, 304, that's got to be cocaine, but I'm going to run through these scans. Okay, and as this peak fades and the next peak grows in, we are going to see, so right here, we have both the cocaine and the heroin right here. You can see, and if I zoom in on where we are right here. We have a little bit of cocaine, a little bit of heroin. It didn't come all the way down. The 304 didn't go all the way away, and then the 370 rise up. They're not completely resolved. Now, as I go up, I can see the cocaine there's still a little bit of cocaine left over in here, but the peak that we're seeing is for the heroin. And then you can see right here, this is a mix of the 2 things. We do not have baseline resolution, so there's a mixture of the benzylecgonine here and the heroin at 370 here. So a powerful trick that you can do with this is if you say, okay, I got a really complicated chromatogram. I had a bunch of stuff in there that I did not anticipate. I want to get really good signal to noise. And sometimes you can have a peak that's just buried in the noise and you don't even see it. But if you know what you're looking for, you can say, you know what? Just show me the signal for 304. Just show me the signal for cocaine. So I'm going to click on 304 right there. I'm going to say, instead of right now it's set to every point, the Y intensity for every point right here is the tallest peak in the spectrum, the base peak. But what I'm going to say now is, I'm going to say, don't just pick the base peak. Don't pick the tallest peak in the spectrum. Only show me the signal for 304. Plot the entire chromatogram as the intensity of the signal at 304, and look at that. Everything else is gone. This is the same data. I haven't run a new run. I've just changed the way that I show the chromatogram. And now I can beautifully see. So I get to actually see, you can see the reason we saw the cocaine in there is because it's still tailing. It's still coming down when that other peak rises up. Okay. I can do the same thing for the heroin. I can say, you know what, also show me this chromatogram, but show me it just for the 370. And then look at that. We've pulled these peaks apart. And then I can say, also just show me the benzylecgonine. Look at that. We have these 3 separate peaks here. But you can see now, at this point, there's still leftover cocaine here. And heroin is starting up. The cocaine's fading away. Here's the heroin. And then the heroin is fading away here. And the benzylecgonine is coming in. So the mass spectrometer is really powerful in concert with chromatography. And that's going to be the most popular instrument in all of forensics, actually, is combining mass spectrometers with chromatography. The GCMS is the most popular for most of drug chemistry. LCMS is the most popular for forensic toxicology. That's not just because of what you can do here. It's related to that. There's a trick called MSMS you can do that dramatically improves the sensitivity. But the UV and the MS detectors are both powerful because you can get, those are going to be by far the most common detectors for LC. But as you click through your chromatography, you also get information, you get spectra at each point that gives you some idea of what you're looking at. And after having run GC and not knowing what all these peaks are, you can imagine how handy that is. If you're just looking at a peak, you don't even have to run a standard, and you can be like, what is that thing? And you can click there and go, oh, 304, that's probably cocaine. Oh, this guy, 318. That's actually, I don't remember what that is. But you can get a really good idea of what these guys are based on their molar masses. And you can plot the chromatogram in different ways to enhance the signal to noise for specific compounds that you're looking at. So a mass spectrometer is going to be a really powerful detector. Most people, when they buy an LC, if you have the money, you get the mass spectrometer is more expensive than the LC. It's more like you buy a mass spectrometer and you purchase an LC on the side with it. An LC with a UV detector, it's almost always going to be the photodiode array. There is another arrangement we'll talk about later in the semester, a scanning instrument, but almost all UV detectors for LC are photodiode arrays. There are a lot of different types of mass spectrometers that you can connect to an HPLC, but if you can afford it, mass spectrometer is the best detector for most things coming out of the LC, because you get a lot of information about the peaks in the chromatogram. It's very good information, and for some of the mass spectrometers, it can push you into category A. So the downside of the mass spectrometer, we're going to get more into that in mass spectrometry. They're expensive. That's one of the things that keeps them out of a lot of crime labs is LCMS. The mass spectrometers that go with LCMS are more expensive than the mass spectrometers that go with GCMS. Another thing is that it depends on the kind of mass spectrometer you're using, but for the most part, just like with UV, if you don't have amines, carboxylic acids, things that can have charge, so amines accept protons really easily. So they work really well for this kind of mass spectrometry. You can put protons on a lot of different things in mass spectrometers, but certainly things like alkanes, aliphatic hydrocarbons, they are not going to work well at all with this type of mass spectrometer. So it tends to be that really non-polar compounds, or compounds that have a lot of hydrocarbon content, are mostly hydrocarbons, are not going to do very well on LCUV or LCMS. And there are very few LC detectors that they will do well on. There are some specialty LC detectors that can sort of function with things that have no chromophores and don't form ions very easily, but we are not going to go into those because you almost never see them used in forensic science. Okay, so we covered some of the definitions of vocabulary associated with HPLC. We talked about columns, their dimensions. We talked a lot about the particle size and the phases that determines the chemistry of the stationary phase. And then we talked about some logistics for the pumps, which are really important because they output the pressure and they push the solvent, the mobile phase, through the stationary phase. We also talked about injectors and getting a nice injection with an auto sampler, and then how you can use that pump and the mixer to get different mobile phase compositions, to do different percent isocratic runs or gradients if you want. And then we talked about UV and mass spectrometers as detectors, and looked at some example data, and even saw how you can use the spectra from the UV-Vis or the mass spectrometer to get information about specific peaks in the chromatogram, or change the view of the chromatogram to get more information.